right, folks, so this is where we had left off in lesson 4. So we had already covered the part about what population density is and how you calculate and record it and how you could describe it by looking at different distribution patterns. Now we're going to talk a little bit more about changes. So density is something that's sort of a static measurement. Right now, at the time we're measuring, how many are there in a particular area. But the next few things that we're going to look at really have to do with the idea of change. So we're going to consider population size. Now, population size on your data sheet is represented by, I'm going to be risky here, N. Oh, that was close. N, that's population size. That's one of the letters that's described on your data sheet. And there are different things that can contribute to the size of a population. These 4 that are listed are the typically referred to ones in questions that you might answer. Natality is something that could change the size of a population. Natality refers to the number of births. So in my fictitious example down here, we're going to say that there were 5. Immigration, which we've already mentioned because it's an example of migration. It was one of the things that could cause changes to gene pools. Not having migration was one of the Hardy-Weinberg conditions. But immigration is the arrival of new individuals in a population. In my fictitious example, we'll say 6. These first 2 factors both increase the size of a population. People are born or people arrive from somewhere else. The next 2, mortality and emigration, are both things that would decrease the size of a population. Mortality refers to deaths. In my fictitious example, we'll say 7. And emigration refers to exit. So immigration is new people coming in, immigration in. Emigration is exit, emigration exit. They both start with E. So in my fictitious example, we'll say that 8 people emigrated from the population that we're considering. Now, population size is N, but the other part of this is, well, that's pretty decent, is change. And you might remember from other science courses that anytime we want to represent change, we use the delta symbol, the one that looks like the triangle. So change in population size, change delta, population size N, delta N. One of the ways we can figure out the change in a population size is to take the factors that increase a population, like natality and immigration, add them up, and subtract from them the factors that decrease a population. Now, if you have your data sheet handy, I'd like for you to take a look at it just for a moment. On your data sheet, it says, so I'm looking at this side here, not the side with the mRNA table, but the other side. But it says on your data sheet that change in population size, delta N, equals factors that increase population minus factors that decrease population. But it doesn't say what the factors are. I'm telling you these are the factors. So these are not on your data sheet. On your data sheet it just says increase and decrease. So you need to know natality and immigration go on the increase side. Mortality and emigration go on the decrease side. Okay? That you need to know. I always notice that M and E go together and it spells the word me, and that seems easy to remember. So anytime you can give yourself a little trick to remember what goes where, it's useful. So in this little fictitious scenario where I said 5 people were born, 6 people immigrated into the population, 7 people died, and 8 people left the population. If I wanted to calculate delta N, the change in the population size, I would do 5 plus 6. those two factors that increased my population size. And I would subtract 7 plus 8. The 7 plus 8 is in brackets, which means you add them together first before you subtract. So I have 11 minus 15. That means that delta n was minus 4. The change in the population was minus 4. So in this population, whatever I started with, I have 4 less individuals at the end than I did before. Notice that this isn't telling me the total population size, just the change. What's the change? That's why we have the delta. Now, very often, you won't be doing this all by itself. It will be part of a bigger question where we're trying to consider the change in population size over time, or maybe compared to something else. So this is often just one small piece of a bigger puzzle. So before we go there, does anyone want to ask anything about this? So we're going to take a look at a few calculations that have the word rate in them. Growth rate, and then on the next one, per capita growth rate. Growth rate is defined as the effective change in a period of time. The formula for growth rate is on your data sheet, so you do not need to memorize this formula, but you have to know how to decide which number goes where. Now there's two different ways that you could find delta n. One of them is the one that I just showed you. The other one is by simply taking the final population size and subtracting the initial population size. Very physicsy here. If you remember, maybe you've been in physics or you remember in Science 10 doing like delta t or delta d over delta t to find speed, where you did final minus initial. So up here, where I'm trying to find delta n, I might do final minus initial population size, right? N is the size of the population, F means final, little I means initial. Or I might find delta n the way that I just showed you. Either way is acceptable, and it'll really just depend on the context of the question. For time, always final minus initial. We'll usually be measuring time in years, and we'll always make the assumption that it's from the same exact point in each year so that it's a full, complete year. So in my first example, I'm saying that in 1997, there were 3,800 snails, but in 1999, there were 1,800. And so if I want to figure out the growth rate of this population of snails, here's my formula. Delta n over delta t. So what's the change in the population divided by the change in time? In this scenario, I don't know how many were born and how many died. I could probably infer it, but I do know the final and the initial population. Time only goes one way, as far as we know, and so the later year is always the final population, whether that's the bigger or the smaller number. Trust me, your brain is going to want you to put 3,800 first because it's bigger. But please recognize that a lot of the time, populations get smaller. And so it is perfectly reasonable to have a negative answer. If your answer is negative, numeric response questions don't let you put a negative symbol in. So there would always be like a negative symbol in front of it or something that says plus or minus, so that you know that your answer could be negative. In this case, my final population was 1,800 snails. My initial population was 3,800. Time will always be the later year minus the earlier one. So if I simplify that, I have negative 2,000 snails per 2 years. Like with density, I'm going to use the units that the question gives me. Most questions will give you years, but it could be reasonable to have hours or months as well, depending on the organism. But you don't have to change the units. You just use the units the question gave you. When I do this division, negative 2,000 divided by 2, I get negative 1,000 snails per year snails per year. That's what I divided, so that is my unit. Now, a lot of the time people are like, well, I can do that. It's a pretty straightforward calculation. And here's where it will get tricky. Growth rate is not the only calculation that we'll do. There's another slightly different but sort of similar calculation. So it's really important that you read the question to find out what it's asking you.
Sorry, can I see that just for a minute longer?
You sure can. Anyone else want to ask anything here? Yeah.
So, in the equation after like trend and
Yep.
then what's this saying?
Like NF minus NI.
And then what is the bottom?
Delta T, TF minus TI. So the same thing that was up here. That's one way you can find a delta. A lot of the time it'll be final minus initial. That's what the F and the I represent. For delta N, it might also be the other method that I showed you on the last slide. So I'm just trying to make sure you see all the possibilities for finding the change in population. Did that clear that up for you, Kim? Okay. You're welcome. Now here's the other side of the story. Per capita growth rate. This is the change in population size, but not over time. It's the change in population size compared to the original population. Okay? So it sounds similar, but it's not the same. The formula is also on your data sheet. So you do not need to memorize CGR equals delta N over N. But you do need to recognize when do you use this formula and when do you use the other one. So in my example, we are going to talk about a village of 1,000 people. That is the initial population size. There were 1,000 people. Then there are 50 births, 30 deaths, and no immigration or emigration. This is a very fictitious place where no one leaves and no one new comes. It sounds a little bit haunted. And it happens during 1 year. A lot of the time, questions will give you enough information to calculate both growth rate, which is over time, and per capita growth rate, which is it, which makes it tricky because you have enough numbers to calculate both things. In this question, we're going to compare the growth rate and the per capita growth rate so that you can see how they differ. So I started out by saying, well, N is 1,000. That's my population size. I also know that there were plus 50. That was natality. Mortality was minus 30. So my delta N will be 50 minus 30. In other words, plus 20 people. That's the change. Notice I didn't say that was my final population size. That was the change. That's how many people the population changed by. So in this example, I calculated the change in population not with final minus initial, but with that first strategy. So I can calculate growth rate. It said it was over 1 year. And if I want to calculate growth rate, I take delta N, the change in the population. Not the total population, but the change. In this case, I had already calculated it. It was plus 20 people. My time, it said that it was 1 year. So sometimes questions will give you a start and an end date, and sometimes we'll just tell you flat out, this is how much time passed. In this scenario, I told you it was during 1 year. That's the change in time, so we don't have to calculate it. So my growth rate in this scenario would be plus 20 people per year. If we compare that to the CGR, the per capita growth rate, the formula is very similar. Delta N, the same delta N that I calculated, is on top. But the bottom number in the formula is not time. It's N, my original population size. My original population size was 1,000. So my calculation is 20 over 1,000. When I calculate that, it gives me 0.02, very small. And this is a pretty typical thing. The per capita growth rate is very often a small number. It's often much smaller than the growth rate over time because we're comparing it to the total population size instead of just to time. The unit for per capita growth rate will always be organisms per capita. In this case, it's people per capita. If we were talking about lions, it would be lions per capita. If we were talking about penguins, it would be penguins per capita. But that's always how we'll represent it. And like with other numeric response questions, the unit will always be indicated at the end of the dashes for the numeric response. So you shouldn't have to guess what the units are. So I would like for you to try doing this second question. So folks, just because the smartboard is not going to let me write this in any way that's going to look legible to any of you, I've written it on the whiteboard. If I want to calculate the growth rate, I needed to know delta n. Delta n is the change in population. So remember, it's not what's my new population size, it's how much did it change by. So I figured delta n out over here. You don't have to do that as a separate step. I just wanted it to be clear. In this scenario, I didn't know births and deaths, but I knew the final and the initial population. So I did 2,300 minus 2,000. It gave me 300 deer. You don't have to write a plus. I like to do that just to confirm for myself that it was in fact a positive number as my answer and not a negative one. So I took this 300 and I put it as delta n in my growth rate formula. It said it happened over 1 year again. It's not always going to be 1 year where the calculation is easy to do in your head like that. I just like to make it easy sometimes when we're doing examples like that. That means that my growth rate is 300 deer per year. Now my per capita growth rate is going to be different. I'm going to use the same delta n, this same 300 deer. So notice, it's the same value in both of those calculations, but the number on the bottom is different. The number on the bottom is always whatever my initial population size was. So initially, there were 2,000 of them. Not at the end where the change had happened, but initially. And it's important to always put the initial one here. If it was a multiple choice, one of the wrong answers would be the number that you got if you put 2,300 there instead of 2,000. If you have this, 0.15 deer per capita is the answer that you should get. Now, if you have questions about this example, I would love to answer them. Oh, look at that. I did put it in the slideshow. Fancy me. Here it is on the smartboard and on the whiteboard. Now there are a couple more examples that are in the note package. The first one is a pretty straightforward example. The second one shows you what you have to do if growth rate is not the thing you're trying to calculate. It's not common or typical, but every once in a while you have to find a different value in the formula than the one that's given. So I'm going to pause here then. The first one is about these cute little things, collared pikas. They're like little rodents. They're not cute. They look like gophers or other things of that nature. Maybe they're cute. I changed my mind. But the population went from 25 individuals in 1998 to 5 in 2000. This is a question where you have enough information to calculate growth rate or per capita growth rate. And so it was important that you read that the question was asking per capita growth rate. Most common error I see is that people will have calculated growth rate here instead of per capita. Per capita growth rate is delta n over n. Delta n I calculated, like I showed on the side, by doing final minus initial population. Final population is the one in the later year, 5. Initial population is the one in the earlier year, 25. So my change in population, delta n, was minus 20. N is always my initial population size. What did I start with? I started with 25. So CGR is negative 20 divided by 25, which gives me negative 0.8 picas per capita. I'm not saying that it's impossible, but if you got a rather large number as your per capita growth rate, I would second guess myself and be like, ooh, well that's weird. Per capita growth rates aren't usually big numbers. They're usually like these small decimal numbers. They don't have to be less than 1. They have been on these examples, but they're usually pretty small numbers. And so if I got something like, I don't know, 20 as my per capita growth rate, I'd be like, is that my growth rate? That seems kind of bigger. The other question that sometimes comes up is about this negative. If it was a numeric response question, like I said before, the negative symbol would show up in front of it because you can't actually fill in a bubble for the negative. It would also direct you as to how many decimal places you need to put in your answer so that you knew, should I be adding a 0 after the 8 and you need 2 decimal places, or is this okay? Now, does anyone have questions about that first one? I would say that is your typical per capita growth rate style question. The second one is harder because you have to manipulate the formula. It tells me that the per capita growth rate was 75.9. Now, it told me this in the question. So, even though that is kind of big, I noticed that it's over quite a long period of time. So I'm like, okay, that makes sense. Plus, they told me this in the question. It also says my delta t was 25 years. So I have enough information to look at growth rate or per capita growth rate, right? But I have to learn to recognize which information I need. My initial population size, N, or N initial, was 26 caribou. It tells me the per capita growth rate and asks me to calculate the number of caribou at the end of that 25 years. So I'm looking for final population size. Here's my per capita growth rate formula. CGR equals delta N over N. I'm going to replace delta N with NF minus NI, final minus initial population size. That's what I'm looking for. That's why I circled NF. I'm looking for the final population size. So I need to do some manipulation of my formula. I want to take this N and move it to the other side. Since I was dividing, the opposite of that is to multiply. So I multiply it and move it to the other side. That's how I got CGR times N. Now I also want to get rid of N initial here. It's in the way. It was being subtracted, so if I want to move it to the other side, I add it. So I add N initial on both sides. That's where I got plus N initial. So a little bit of formula manipulation. Like I said, I don't anticipate that this is the #1 way a diploma would ask you about it, but they could. It's fair. So what I would do is my per capita growth rate, 75.9, times my initial population size, 26, and then I'm going to add what I started with, 26. The reason I have to multiply and then add is because I need to know the change, and then I need to add the change to the original population. That's how I figure out how many there were at the end. This gives me 1,999.4. And in this scenario, you would round your answer to a whole number because you can't have 0.4 of a caribou. Can't have 0.4. Well, you could, but it wouldn't be alive, I don't think. And you would probably be a hunter and eating it, and there'd be blood everywhere. Now, if you would like to ask a question here, I would love to answer it. Okay.
Sorry, could I see this?
You sure can. Why am I we take a little body break for a minute? If you need to stand up. Okay, so this last thing I want to show you is really just a way that we could represent growth rates and population change. It's more commonly used for people, but we could, I guess, theoretically apply it to any population. If you take a look at these age pyramids, they all have age groups along the side and then percentages along the bottom. Half of the graph will represent males, half of the graph will represent females, and it's really not relevant which one was on the left and on the right. Like, that doesn't really impact things. So we've got 3 example age pyramids up here, and it's really the shape or the general shape of them that I want you to see. The first one from the Democratic Republic of Congo shows rapid growth. What I mean by rapid growth is that the growth rate would be a positive number that's bigger than 0, right? Like, it's not a tiny little fraction, but some bigger positive number. In this scenario, we would say, whoops, I think I put these the wrong way in my excitement with typing. Let's fix that. That mortality would be less than natality. Fix it. Go back to my slideshow. No, that's better. But if the growth rate is positive, what it usually means is there are lots of people being born compared to the number of people who are dying. And that will usually result in a population that is growing. Now notice I didn't give specific values here. I just said, would it be positive, and you'll see here, or 0 or negative? Would mortality be bigger or the same or smaller? That's the comparison that I'm going for. So if I were to represent a population with a growth rate that was positive, that had more natality than mortality, it would look like a triangle. And I drew one up on the board here so that you could see. It's like a true pyramid, large base, pointy top. Now sometimes populations might have really slow growth. Slow growth is a population where the growth rate is either really close to or exactly 0. Probably unlikely that in real life it's exactly perfectly 0, but it would be close to it. It's not positive, it's not negative, it's just 0. In this scenario, mortality and natality would probably be pretty close to even, and that would explain why there's not a big change in the population size. Now for slow growth, if you look on the whiteboard, I drew a rectangle, even though that's not the shape exactly of that particular one. Kind of looks like the Stanley Cup, is what I think. But I'm ignoring this top piece of the age pyramid. Why? Everybody dies when they get older. That's our life expectancy. So I try to focus on the bottom 2/3 of the age pyramid when I'm thinking about the shape. When I look at the top should be smaller on every age pyramid because that's how long humans live. And that would explain why it gets skinnier. So when it's more or less rectangular, where the base isn't considerably bigger than the levels that come above it, that's representative of slow growth. We could also have a population that had negative growth. So where the growth rate was a negative number, they're losing members of their population. Notice I didn't give a number. I'm not saying what the growth rate is, just that it would be negative. In this scenario, mortality is probably higher than natality. More people are dying than are being born. So the population is getting smaller. So my negative growth example comes from data from Germany. This is a few years old already, but I'm guessing it hasn't changed much in the last couple of years. But if you take a look and we focus on the bottom 2/3, is it a perfectly inverted pyramid? No, but it does look skinnier on the bottom and get a bit wider as you go up. That's what negative growth looks like. There are less people in the younger ages, indicating less people have been born. And there are more people in the older ages, leading towards more people dying as we reach life expectancy.